Good day, learners. Welcome to our physical sciences lesson. My name is Amenem Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, learners, today we are going to focus on electrostatics. Remember, when it comes to your physical sciences, you have your paper 1, which is your physics, your paper 2, which is your chemistry. So the focus is physics, and then the knowledge area under physics is electricity and magnetism. Then under electricity and magnetism is electrostatics, right? So, but for today, under electrostatics, we are only going to focus on Coulomb's law. Right. Learners, you grade 11s, you did electrostatics in grade 10. You know that all materials, they contain positive and negative charges. And then some materials, you know, they have equal number of positive and negative charges, or they have equal number of electrons and protons. And then we say those objects or those materials, they are neutrally charged. Yeah? So then some materials, they are positively charged. But if a material is positively charged, or if an object is positively charged, it doesn't mean that it doesn't have, you know, the negative charges or the electrons, but it has more protons than what? Than electrons. So those objects, we say they are electron deficient, or they have shortage of what? Of electrons, right? Then those which are negatively charged, again, it doesn't mean that there are no positive charges there. The positive charges are there, or the protons are there, and we say those objects, they are what? They are negatively charged, or they have excess of what? Of electrons. So it's either you know, an object is neutrally charged, which means that it has equal number of electrons and protons, or is positively charged, right, which means that it has more protons than what? Than electrons, or more positive charges than what? Than negative charges. Then negatively charged objects, they have more negative charges than what? Than positive charges, or they have more electrons than what? Than protons. And then those objects, we say they have excess of what? Of electrons. And then the ones that are positively charged, they have shortage or electron what? Deficient. They have shortage of electrons, or they have electron what? Deficient. So it's what you know from what? From grade 10. So when it comes to objects, all objects, they contain positive and negative what? And negative charges. And then those ones with equal number of electrons and protons, they're neutrally charged. And then the ones that are positively charged, they've more protons than electrons, so which means that they have electron deficient, or they have a shortage of what? Of electrons. And then the one with excess electrons, it means that they're negatively what? They're negatively charged. Then the triboelectric charging. So there are different types of charging objects. So you did that in grade 10, and one of them is triboelectric what? Charging. And then another thing that you did in grade 10, it was the conservation of charge. Then one charge, the symbol for charge, learners, is Q, right? And then the SI unit for charge is coulombs, which is what? Capital letter C. So let's not forget that. And then in grade 10, you also, looked at the principle of conservation of charge. So according to our examination guidelines, this is how we have to state the principle of conservation of charge. The net charge of an isolated system remains constant during any physical process, right? The net charge of an isolated system remains constant during any physical what? Process. So that is the principle of conservation of what? Of charge. You have to know that. It doesn't mean that since now you're in grade 11, so you neglect what you did in grade 10, all right? Then also apply the principle of conservation of charge, all right? Then another principle, it's the principle of quantization of charge. So this is how we have to state it according to our examination guidelines. All charges in the universe consist of an integer multiple of the charge on one electron, right? So there are two, principles here. Is the principle of quantization of what? Of charge, or the principle of charge quantization, and the principle of conservation of what? Of charge. So those are the two what? Are the two principles. And another thing that you need to know, right, so this bullet, when two identical conducting objects having charges Q1 and Q2 on insulated stands touch, each object has the same final charge on separation. So this is what you also did in grade 10. And to calculate the charge after contact, the charge on each object after contact, the equation that we use is this equation, right? Which is Q nu equals to Q1 plus Q2 over 2. So when do we use that equation? We'll use that equation to calculate the charge on each object, or the charge on each sphere after contact. So if objects, they're brought into contact and then separated, then remember, during contact there will be transfer of electrons, right? Until these two objects, or these two spheres, they have the same charge. So how do we calculate that charge? The charge is calculated using the equation Q nu, or Q equals to Q1 plus Q2 over 2, right? So then the principle of quantization of charge, when it comes to the principle of quantization of charge, right, this is the equation, which is Q equals to NQE, where Q is the charge that is transferred during contact, and then N is the number of electrons, and then QE is charge on an electron. It's a constant, and then that constant is 1.6. The value of it is 1.6 times 10 to the power negative 19 negative 19 coulombs, right? Then again in grade 10, you also looked at the forces. So between like charges, there's force of repulsion, and then between unlike charges, there's force of of attraction. Okay, so like charges, they repel; opposite charges, they attract. So that is grade 10. So we're in grade 11, we understand, but what you did in grade 10 is also applicable, or is also examinable in grade 11. So we cannot neglect that. All right, then grade 11, this is the grade 11 examination guidelines. This is what we need to focus on. I said today we are going to focus on on Coulomb's law, right? So under Coulomb's law, this is what we need to look at, according to our examination guidelines, is to state Coulomb's law, and this is how we have to state it, right? Okay, before that, so let me just go through those bullets. Is to state Coulomb's law, solve problems using the equation F equals to K Q1 Q2 over R squared for charges in one dimension, and also solve problems using the equation F equals to K Q1 Q2 over R squared for charges in two dimension, right? For three charges at right angled formation. All right, then this is actually what we need to focus on under Coulomb's law. That is grade 11. All right, but I'm saying to you, let's not neglect what we did in in grade 10. So while I will be doing questions on Coulomb's law, but I will try by all means also to to include some of the things that we did in grade 10. For example, calculating the net charge, calculating the charge on each sphere after contact, calculating the number of electrons that are transferred from one sphere to another sphere, which sphere has electron deficient, or which sphere has shortage of electrons, which sphere has excess of electrons. Can we be able to calculate the number of electrons in each sphere? So those are the things that we are going to to include while we are busy with Coulomb's law. All right, so according to our examination guidelines, this is how we have to state Coulomb's law. Coulomb's law states that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. The magnitude of the electrostatic force exerted by one point charge on another point charge, it is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. So this is how we have to stage, Coulomb's law in weights according to our examination guidelines. I know you did, Newton's law of universal gravitation. Then it's almost the same, but it actually is not the same, So when it comes to Newton's law of universal gravitation, you talk about masses, right? But here, when it comes to Coulomb's law, we talk about what? About the charges. So remember, this is electrostatics, which is the study of stationary charges, all right? So here we talk of, charges. So immediately when you mention masses instead of charges, you are going to get 0 out of 2 marks, So when we mark this, this definition, it's either 2, sometimes it's marked independently, all right? So there will be a first mark for this part, the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to what? To the product of the magnitude of the charges. You will get a mark there, all right? And inversely proportional to the square of the distance between them. That is another mark. But if you are going to mention, charges instead, masses instead of charges, you are going to get 0 out of 2 marks, all right? So please be careful. Here, we talk of charges. Then when it comes to Newton's law of universal gravitation, we talk of what? Of masses. So please, learners, let's not confuse the two. And again, let's not confuse the two equations, right? So this equation, right, this is the equation that we use, right? According to your data sheet, right? So this is the equation, okay? So this is the equation. So it's F equals to KQ1, Q2 over what? Over R squared. But when it comes to Newton's law of universal gravitation, it's F equals to G M1 M2 over what? Over R squared, okay? So I hope you can see the difference. So here we talk of what? Of charges. So please do not confuse the two equations, right? So then, maybe before we look into that, right now let's look at the relationship between, the electrostatic force and the product of the charges, okay? So according to the law, right, the relationship between the electrostatic force and the product of the charges is directly what? Proportional. So what is the meaning of directly proportional? It means that if the product of the charges increases by the factor of 2, even F, or the electrostatic force, increases by what? By the factor of what? Of 2. So that is the meaning of directly what? Proportional. If this one increases by the factor of 5 or 6, even the other one will increase by the factor of 5 or what? Or 6. So that is the meaning of direct proportionality. All right. So now let's look at the relationship between what? Between the product of what? Of the charges and what? And the electrostatic force. So the electrostatic force depends on what? On the product of the charges. It also depends on what? On the square distance between the centers. So on the square distance between them, all right? Because we are talking about what? About the point charges, right? So what is the relationship? According to the law itself, it says electrostatic force is directly proportional to the what? To the magnitude of the product of what? Of the charges, okay? Or to the product of the magnitude of what? Of the charges, all right? So then we can also, represent that relationship using a graph, all right? So this is the graph of electrostatic force, which is measured in newtons versus the product of the charges. And then product of the charges, each charge, remember, the SI unit for charge is Coulomb. So here is Coulombs times Coulombs, which will be Coulomb squared, all right? So let's look at the relationship. The relationship is directly what? Proportional. So this is the graph that shows the direct proportionality between the product of the charges and what? And the electrostatic force, all right? So which means that if Q1, Q2 increases by the factor of 2, even F, which is the electrostatic force, will increase by the factor of what? Of 2. That is the meaning of direct what? Proportionality. So this is the graph that shows the relationship between what? The force, which is the electrostatic force, and the product of what of the charges. Then when you look at the graph, so learners, paper 1, it's full of graphs, right? So you must understand how to interpret graphs. For example, if you're given a graph like this, right? One, you must identify, the variables, the dependent variable, the independent variable, right? So the dependent variable here is the electrostatic force. So this one will be the dependent variable. All right, and then Q1, Q2 will be the independent variable. It's what we are manipulating, or is what we are changing. Independent. Right, so we have dependent and independent what variable, right? So, and also what the controlled what variable here, the controlled variable, it should be what the distance, okay? So the distance between them, that will be the controlled what variable. The distance between them, that will be the controlled what variable. Controlled, it is going to be what the R or the D, distance or what, or D is the distance, R is still what? The distance. All right. So that is what the variables, the dependent, the independent, and the controlled what variable. Then another thing that you need to look at, when we are dealing with graphs, one, I said, is the variables, the dependent variable, independent variable, the controlled variable, and then two, the physical quantities represented by the gradient and the area, right? So in most cases, you'll find that a gradient represents a certain physical quantity, but area, there's no physical quantity represented by area under that graph, right? Or in some graphs, you'll find that there is a physical quantity represented by the what? By the area, but there is no physical quantity represented by what? By the gradient. So you need to check those things, right? So if they say use the graph, right? So one, they will ask you about the dependent, the independent, the controlled, then again, maybe they can even ask you about what here, the investigative question, and also what the conclusion. So the conclusion here will be, you look at the graph, right? The conclusion will be looking at the graph, your graph starting from the origin. So the conclusion will be that electrostatic force is directly proportional to what? To the product of the magnitude of what? Of the charges, right? Or as the product of the magnitude of the charges increases, the electrostatic force also increases. So those are the things that we need to look at if you are given a graph. Identify the variables, right? And then check the physical quantity represented by area if it is there. Check the physical quantity represented by the gradient, right? So one of the two is either there is a physical quantity represented by the gradient, there is no physical quantity represented by the area. Or there is a physical quantity represented by the area, there is no physical quantity represented by what? By the gradient, right? And then from there, the conclusion based on the graph. For example, what could be the conclusion here? Your conclusion must also show, the relationship between what? Between the dependent and the independent what? Variable. For example, in this case, as the product or the product of the magnitude of the charges increases, what happens to the electrostatic force also increases. Or the electrostatic force is directly proportional to what? To the product of the magnitude of what? Of the charges. Now, let's look at the gradient, right? Or the physical quantity represented by the gradient of this graph, all right? So, the physical quantity represented by the gradient of this graph actually is just K over what here? Over R squared. Where did we get that K over R squared, right? So the equation here, we are dealing with electrostatics or Coulomb's law, which is F equals to what? K Q1 Q2 over what? Over R squared, okay? So your vertical axis, we have F, and then horizontal axis, we have Q1 Q2, right? Then according to your mathematics, right, this is a straight line. We know the equation of what? Of a straight line. The equation of a straight line is y equals to what? Mx plus what? Plus c. Right, so our c, since our graph starts from the origin, our c in this case will be what? Will be 0, because c, remember, is the y-intercept. So you have y equals to what? Mx, all right? So it's y equals to mx plus 0, which will be y equals to what? Equals to mx. Then what is it that we need to do? We need to arrange this equation in a form of y equals to mx plus what plus c, or in a form of y equals to mx, right? Making sure that our y it's what is f, and then our x is what is q1, q2. So if we arrange, we have f equals to what? K q1 q2 over r squared. It will be k over r squared q1 q2. This is y equals to mx. Remember, our x should be q1 q2. Our y should be what? Should be f, which means that the gradient of this graph represents k over what? Over r squared. Okay, so it means that if you are given a graph like this, because it might happen that we can get a graph like this, all right? So if this graph here shows, you know, the relationship between the product of the of the charges and what and the electrostatic force, or electrostatic force and the product of the charges. One, I said to you, identify the variables, all the variables, dependent, independent, controlled, name the conclusion, all right? And then the investigative what question. Then from there, the gradient represents which physical quantity. The area under that graph represents which physical quantity. So in this case, it represents what? K over r squared. So which means that you can use this graph. You can use this graph to calculate the distance between the point charges, right? You can use this graph to calculate the distance between what? The point charges. How are you going to do that? First thing that you need to do is to calculate the gradient, right? And for you to get the gradient, you need how many points? 2 points, all right? So in this case, your gradient will be what? Your gradient, how do we calculate gradient? Gradient, right, gradient here will be change in f over change in q1, q2, right? So we don't have y here. Instead of y, we have f, right? According to your maths, right? How do we calculate the gradient? Is change in y over change in x. In our y-axis, or in our vertical axis, we have f. In our horizontal axis, we have what? q1, q2. So that is why there I'm having change in f over change q1, q2, which will be what? Final f minus initial f, right? Over q1, q2 final minus q1, q2 what? Initial. So you need how many points? 2 points. Then after calculating the gradient, then this gradient, for example, let's say the gradient is let's say the gradient, maybe the gradient that you get here is 5, right? So gradient is k over r squared. So the gradient is what? Is 5, for example, all right? Then equals to k over r squared. So it will be 5 equals to, what is k? K is a constant. The constant is there on your data sheet, right? And according to your data sheet, your k is 9 times 10 to the power 9. Over what? What is your r? It's what we are looking for. Then find r. So here multiply by r on both sides. So it will be r squared. Then your r will be the square root of 9 times 10 to the power 9 over what? Over 5. Then you'll get the distance between the point charges in what? In meters. So this graph, we can use it to calculate, you know, the distance between the point or the point charges, all right? So these are some of the things that you need to know. It's not just about the relationship, just knowing that, the relationship between the product of the charges and F, or the electrostatic force, is directly proportional. You must also be able to represent that relationship using a graph, right? So when you use a graph, what is your dependent variable? What is your independent variable? What is your controlled variable? What is the physical quantity represented by the gradient of that graph, or what is the area represented by the gradient of what of that graph. All right, so those are some of the things that you need to look at when you are dealing with what, with graphs. Okay, then let's look at the relationship between, okay, before that, let's check if now you are given something like this. It's still on the relationship between what, the force and the product of what, of the charges. So for the two charges placed at a distance r apart, the electrostatic force they exert on each other will be F equals to K Q1 Q2 over what, over R squared. So if you want the magnitude, right, of the force that the 2-point charges exert on each other, this is the equation that we have to use. F equals to K Q1 Q2 over R squared, where F is the electrostatic force measured in newtons, and then K is a constant, which is 9 times 10 to the power 9, and that constant is there on your data sheet, so there's no need for you to memorize that equation, right, or that value. Okay, even the equation itself, it is there on your data sheet. Then what is Q1 Q2? Q1, that is the charges, and the charge is measured in what, in coulombs. So it's coulombs, and then here is what is the distance between the point charges, which is measured in what, in meters. So for the two charges placed at distance r apart, their force, or the magnitude of the force, is given by F equals to K Q1 Q2 over what, over R squared. Then if one of the charges is doubled, so now one of the charges is doubled, the electrostatic force will also be what, be doubled, because the relationship between the two is what, is directly what, proportional. So but how do we get that? Okay, mathematically. All right, so if the 2-point charges, they are placed at distance r apart, this is how we can get the magnitude of the electrostatic force they exert on each other. All right, is this one. Then now the distance, sorry, one of the charges is what, now is doubled. Okay, so if one of the charges is what, is doubled, let's find the new force, right, that they exert on each other. So it would be K. One of the charges is what, is doubled. That is why there's 2 there. Okay, one of the charges is doubled, and then Q1 Q2 over what, over R squared. Okay, so this is the same as, right, 2, okay, 2 K Q1 Q2 over what, over R squared. So what is K Q1 Q2? K Q1 Q2 is what, is F. That is why there we are having what, twice F. Okay, so if one of the charges is doubled, what will be the magnitude of F? F is also going to be doubled. If both of them, Q1, Q2, the both charges that are doubled, it will be 2 times 2. Then that will be 4, which means that even F will be what? Will be 4. So that is just a relationship between what are the electrostatic force and the product of what? Of the charges. Right. Now let's look at the relationship between the electrostatic force and the square distance between the centers. Right. So the relationship, according to the law itself, it says that the force, or the electrostatic force, is inversely proportional to the square of the distance between them. It is inversely proportional. We know the relationship. So we are showing the relationship here between the force, or the electrostatic force, and the square distance between the charges. All right, then this is the graph that shows direct proportionality between F and 1 over what, over R squared. Okay, then so there's direct proportionality between the two. So one, they can ask you that about the dependent variable. What is the dependent variable? In this case is your F. The independent variable is 1 over R squared, is what we have as on your horizontal axis. That is the independent variable. And then the controlled variable in this case will be what? The magnitude of the charges, all right, according to that equation. So just use that equation. So here we are focusing on F and 1 over R squared, right? So it means that Q1, Q2, those are the constants, okay? Then for the previous one, we are focusing on what? On F, Q1, Q2. So the controlled was what? Was R, which is the distance, okay? So here it's F and 1 over R squared. So according to that equation, what is kept constant is Q1, Q2. All right. So those are the constants, right? Then this is the graph that shows the direct proportionality between F and 1 over R squared. So another thing that we need to look at here is the physical quantity represented by the gradient. So the gradient, this is a straight line, so y equals to mx plus c. So our y should be F, and then our x should be what? 1 over R squared. So the equation is F equals to K Q1 Q2 over what? Over R squared. That is the equation. So we arrange this equation or manipulate this equation in a form of y equals to mx, making sure that our F or our y actually is what? Is F, and then our x is 1 over what? Over R squared. So already our F is the subject of the formula, which is y. So it's F equals to what here? It's equals to K Q1 Q2 multiply that by 1 over what? Over R squared. So it's y equals to mx. Our x should be 1 over R squared. Our y should be what? Should be what? F. Then which means that the gradient represents what? K Q1 Q2. So if you can calculate the gradient here, you will get the charge, right? If you can calculate the gradient. So for example, if the charges here, they're identical, right? If they're identical, it means that if they're identical, for example, let's say you calculate gradient. The gradient, let's say again, is 5. So it will be gradient equals to K Q1 Q2, right? Then 5 equals to 9 times 10 to the power 9. Then this is going to be what? Q squared, because they're identical. Then you find the value of what? Of Q. So your value of Q will be what? 5 over 9 times 10 to the power what? 9. That will be the square root. Then you'll find your answer in what? In coulombs. So you can use this graph to get the charge, right? If, for example, we told that these charges are what? Are identical. All right. So this is the graph that shows the relationship between what? The force and the square distance between the centers. All right. Or the square distance between the point charges. All right. Then a mathematical relationship, right? For the two charges, each placed at a distance r apart, the electrostatic force they exert on each other, we all know that by now, that the electrostatic force that they exert is K Q1 Q2 over R squared. Then now, if the distance is doubled, how will the magnitude of the electrostatic force change, right? So the distance is doubled. Q1 Q2 is still the same, so that is why here I'm having K Q1 Q2. Then the distance is doubled. That is why you see 2 there. All right. So the distance is doubled. So it's what here? 1 over. Where is this 4 coming from? Is 2 squared. So 2 squared is what? Is 4. So here I'm having 1 over 4, right? And then where is this R squared coming from? R to the power 2, which is going to be what? R squared. So I'm having 1 over 4. K Q1 Q2 over what? Over R squared. So it's 1 over 4. What is K Q1 Q2 over R squared? K Q1 Q2 over R squared is what? Is F. That is why the magnitude of the new force, it's going to be what? 1 over 4 F, which is the original what? Original force, right? So that is the relationship, the mathematical relationship between the electrostatic force and what? And the square distance between them. All right. So you have those two graphs. So you should know the relationship between the electrostatic force and the product of the charges, and you must be able to represent that relationship using a graph, right? So if you are given a graph, what is the strategy? Identify the variables, check the physical quantity represented by the gradient or the area, right? Conclude based on the graph. All right. So those are the important things that you need to to look at when you are dealing with graphs. Okay. Then another thing which is very, very important when it comes to your electrostatics is the conversion of units. All right. So remember, according to that equation, F equals to K Q1 Q2 over R squared. Q, it is what? The charge, and the charge is measured in what? In coulombs, right? So it's not always the case that you'll be given charge in coulombs, you know. So they can give you charge in millicoulombs. They can give you what? Charge in microcoulombs. They can give you charge in what? In picocoulombs. And they can also give you what? Charge. So this one, it's nano. So here it's supposed to be, let me rectify this. It should be nanocoulombs, so it's NC. So here it should be NC. And then here it's 1 NC equals to, so here it's 1 NC, which is 1 times 10 to the power negative 9 what? Coulombs, all right? Then we also have what? Coulombs to coulombs, right? So picocoulombs to coulombs, it's 1 picocoulomb equivalent to 1 times 10 to the power negative 12 what? Coulombs, right? So it's not always the case that you will be given what? Charge in coulombs. So if you're given charge in millicoulombs, convert those millicoulombs to coulombs. How? 1 millicoulomb is equivalent to 1 times 10 to the power negative 3 coulombs, right? Then if it's in microcoulombs, so convert it to coulombs, and 1 microcoulomb is equivalent to 1 times 10 to the power negative 6 coulombs, right? If we are given the charge in nano means 9, right? So in nanocoulombs, then 1 nanocoulomb is equivalent to 1 times 10 to the power negative 9 coulombs. Picocoulombs, so if you are given charge in picocoulombs, 1 picocoulomb is equivalent to 1 times 10 to the power negative 12 what? Coulombs. So these are some of the things that are very, very important when we are dealing with that equation F equals to K Q1 Q2 over what? Over R squared. Then again, the issue of the distance. It's not always the case that you'll be given distance in meters, but remember, according to that equation, we need the distance in meters. So if you're given the distance in millimeters, 1 millimeter is equivalent to 1 times 10 to the power negative 3 meters. If you are given the distance in centimeters, 1 centimeter is equivalent to 1 times 10 to the power negative 2 meters, right? And if you're given the distance in kilometers, 1 kilometer is equivalent to 1 times 10 to the power 3 what? Meters. All right. So that is very, very important. So negative 3, it means that you are dividing by 1,000. Negative 2, you are dividing that value by what? By 100. And then to the power 3, we are multiplying that by 1,000. All right. So according to this equation, F equals to KQ1 Q2. KQ1 Q2. K, it's a constant. What is that constant? Where is K? K is here. It is always what? 9 times 10 to the power 9 newtons square meter per what? Per coulomb squared, right? Okay, that is how, actually that is the value of K. It's a constant, right? Then this Q is always in coulombs. This other Q is always in what? In coulombs. This R, which is the distance between them, right, is always measured in what? In meters. So if it's not in meters, convert. If the charge is not in coulombs, you also need to do what? To convert. All right. Then that is the equation that we are only going to deal with today, right? So let's look at the multiple choice questions. And this multiple choice question, it deals with what? Actually checks your understanding of the proportionality between F and the product of the charges between F and also the square of the distance between them. All right. So two small identical metal spheres on insulated stands carry charges negative Q and positive Q respectively. All right. When the centers of the spheres are a distance d apart, the spheres exert an electrostatic force of magnitude F on each other. So they exert this force, and F we know is given by K, Q1, Q2 over what? Over R squared. Okay? Then But the charges here, you have K. The first charge is just Q. The second charge is what? It's is 3. So it's 3 what? Is 3Q. Over what? Over R squared. So what am I having here? Here I'm having what? 3 K Q. This can be Q1, it doesn't matter. K Q1 Q2 over what? Over R squared. That is F, right? According to this statement. So what is F according to this statement? Is 3Q1 Q2 over what? Over R squared. Where is this 3 coming from? From the statement, they're saying each charge, so the first one carries a charge of negative Q, and then the second one is positive 3Q, right? So I'm having Q there, I'm having 3Q there, and then divided by what? By R squared. So this is what I have, okay? Then, what is the equation? Okay? The spheres are now made to touch and are brought back to the same positions as before. The magnitude of the electrostatic force which the spheres now exert on each other in terms of F will be what? Right. So the two spheres, they are brought into contact. So we cannot neglect that. And if the two spheres are brought into contact, after contact, they must have the same charge. And how do we calculate that charge? We use this equation, right? The equation is Q1 plus, so it's Q1 plus Q2 over what? Over 2. So we are, this equation, we are using it to calculate what? The charge on each sphere after what? After contact. Ne? So what was the original charge? Negative Q, and then plus what here? Into plus what? Plus 3Q. Okay? Over what? Over 2. So I'm having what here? Negative 2 plus 3Q, which is going to be what? 2Q over what? Over 2, which is going to be what? 1Q, which is just Q. All right. So what will be the charge on each sphere after contact? It will be Q. All right. The charge on each sphere after contact will be Q. So sphere A will be Q. Sphere B will be what? Will be Q. Right. Then what will be the force now? The force will be KQ. Remember, it's Q1, Q2 over what? Over R squared. So here is just KQ1, Q2 over what? Over R squared. Okay. So this is what I have now. So they are looking for what here? The magnitude of the electrostatic force which the spheres now exert on each other after the contact. Okay. So the original charge, so not the original charge, but the original F, all right? The original F is this one. Is 3KQ1 Q2 over what? Over R squared. Okay? Now we are looking for F nu. So the original is 3KQ1 KQ1 Q2 over what? Over R squared. Now let's look at the new F. So F nu, which is this one, ne? So new F, okay, it will be what? New F, I'm having the original one is F equals to 3K Q1 Q2 over R squared, okay? Then this one, this is KQ1 Q2 over R squared. See, if I can make KQ1 Q2 over R squared the subject of the formula, I'm going to have what? I will divide by 3, so I will have F equals, sorry, F over 3 equals to what? KQ1 Q2 over what? Over R squared. Okay? Then what is KQ1 Q2 over R squared? Is F over 3. Ne? So here, where there is KQ1 Q2 over R squared, I can substitute by what? By F over 3. So F nu, right, will be where there is k q1 q2 over r squared, I can substitute by what? By F over 3. Okay, so which is the same as 1 over 3 what? F. That is the new F. So it's just maths here. All right, so our answer here will be what? Will be B. Right, so here we're not like the example that I gave you, ne? We're moving from what? From here to, for example, F. We are moving from what? From F k q1 q2 over r squared to something else, which is going to be what? For example, the distance is being doubled, you know, one of the charges is being doubled. What will be the new magnitude of F? So here already we are starting with what? With a force being, you know, increased by the factor of 3, right? So from the factor of 3 to what? To a factor of what? Of 1. So we are moving from there. So it's unlike that example that I gave you. But here is just maths. So these are some of the questions that you will get, and you must be able to, you know, to do them. All right, so it's just maths here. Right, let's look at the second one. Okay, the second one, particle P has charge Q and particle R has charge 2Q. All right, they are separated by a small distance. So you have P, you have Q, right? So they are separated by the small what? Distance, all right? Which is R there. Which one of this one is what? Is Q, and then this one is what? Is 2Q. Okay. So which one of the statements below about electrostatic forces FPR, which P exerts on R, and FRP, which R exerts on P, is correct? Here, learners, there's application of Newton's third law. All right. So the force that P exerts on Q will be equals to the force that Q exerts on what? On P. Right. So the force that P exerts on Q will be equals to the force that Q exerts on what? On P. But acting in opposite what? Directions. So for example here, you are having Q and 2Q. So this is positive, this is positive. So there is force of what here? Of repulsion. So if this dot represents P, right? So there is force of what? Of repulsion between P and Q. So P will move away, right? So this will be the force exerted by what? By Q on what? On P. And then if this dot represents Q, right? If this dot represents Q, then again there is force of repulsion between P and Q, then Q will move away. So why P will move away? Q will move away is because of P, that is being positive. Ne? So it's force exerted by what? By P on what? On Q. Right? So you can see this force and this force, they're equal in magnitude, but you can see they're acting in opposite what? Directions. So the force that P exerts on Q will be equal to the force that Q exerts on P, but acting in opposite what? In opposite directions. So this one is out, and then PR, yes, they are equal in magnitude, these two, ne? But it's like they're acting in the same what? In the same direction. So it cannot be correct. This one is also incorrect, but the correct one will be this one, right? So they have the same magnitude, but acting in opposite what? Direction. You can see that. So the force that Q exerts on P is to the left, and then the force that P exerts on Q is to the right. So they have the same magnitude, but they're acting in opposite directions. So the correct answer here will be what? Will be D, sorry. Right. Then the third one, two identical metal spheres, P and R, on insulated stands. You see, this word is coming, right? Now and then, insulated stands. So why are they placed on those insulated stands? Ne? So the charge cannot be transferred. Charge so the charge cannot be transferred. So these insulated stands, they are preventing charge from, so for this charge not to be transferred, we have to use those insulated stands. So that this sphere cannot lose charge. We don't want this sphere R or this sphere P to lose charge. That is why they are placed on those insulated stands so that they don't lose charge. For example, if it is 2 microcoulombs, it should remain 2 microcoulombs. So to prevent charge from being lost, we have to use the insulated stands. So 2 identical metal spheres P and R on insulated stands carry different charges. The spheres are brought into contact and then separated again. They are brought into contact. What should come to your mind? Q equals to Q1, Q2 over what? Over R squared. The charge on each sphere. The charge on each sphere. That will be equal after what? After contact. So if the charge here is 2, even for R, it's going to be 2, coulombs, right? After what? After contact. Okay. Then, if the charge on sphere R after separation is Q, the charge on sphere P after separation is also going to be what? Q. The charge after separation is also going to be what? After Q. So you should know, right? So if spheres or if objects are brought into contact, right, and then separated. So during contact, charge is transferred, electrons are being transferred until these 2 spheres, they have the same charge. So if the charge on R is Q, even the charge on, on P will be Q after what? After contact. So let's not forget that. Okay, so these were multiple choice questions. Now let's focus on the structured questions, because we'll also get structured questions under Coulomb's Coulomb's law. So 2-point charges X and Y are held 0.03 meters apart as shown in the diagram below. The charge of X is negative 7.2 times 10 to the power negative 9 coulombs, while the charge on Y is plus 7.2 times 10 to the power negative 9 coulombs. What is nice about this question, there is no need for us to convert. The charge is in coulombs, the distance is in what? Is in meters. We are safe. All right. One of the things that they can ask in questions like this, which sphere between the two, or which let's say these were spheres, so which sphere between the two has excess electrons, which one has the shortage of electrons, right? So you can see X is negative, so X has excess of electrons. This one, shortage, is positive, shortage of electrons. Right. So X, excess of electrons, is negatively charged, right? And then Y is positively charged, so obviously it has shortage of what? Of electrons. Another thing that they can ask here, if these 2 spheres were brought into contact, let's say these are spheres, is X and Y, they were brought into contact, electrons, were electrons going to be transferred from Y to X or from X to Y? Obvious, electrons, they're always transferred from a sphere with excess of electrons to a sphere with shortage of what? Of electrons. So electrons were going to be transferred from what? From X to Y. So X to Y. That is how where electrons going to be what? To be transferred. From X to what? To Y. From the one with excess of electrons to the one with what? With shortage of electrons. Okay? So the one with excess of electrons is the negatively charged one. The one with shortage of electrons is the positively charged one, right? Then, which means that if they were brought into contact and then separate during contact, electrons were going to be transferred from X to what? To Y. Then they can even ask you about the force. Is there a force of attraction or repulsion between these two charges? Obviously, here there will be force of what? Of attraction, because unlike charges, they what? They attract. Okay? Then again, they can, that is grade 10, not grade 11. This is just grade 10. Which sphere has excess of electrons? Which sphere has has shortage of electrons? Then, if these spheres or if these objects they were brought into contact, were electrons going to be transferred from X to Y or from Y to X? Obviously, it should be X to what? To Y, from the one with excess of electrons to the one with shortage of what? Of electrons, right? Then they can even say calculate the net charge, right? Remember, according to the principle of conservation of charge, net charge in an isolated system or of an isolated system remains constant during any physical process. So let's calculate the net charge here. Net charge. So I don't want learners to confuse net charge with charge on each object or each sphere after contact. Let's not confuse the two. So net charge is just Q1 plus what? Plus Q2. In this case, then so here the net charge here will be what? Will be 0, right? Because of negative 7.2 and positive 7.2, right? But let's not confuse net charge with what? With charge on each object after what? After contact. So you can calculate the net charge here. So before what spheres are brought into contact, the net charge remains, if the net charge is 0, right? Or if the net charge is 5, before they are brought into contact, even during contact will be 5 coulombs, even after contact will be what? Will be 5 coulombs. Because according to the principle of conservation of charge, net charge of an isolated system remains what? Constant. How do we calculate net charge? This is just grade 10. How to calculate net charge is just the sum of those charges. So Q1 plus what? Plus Q2. All right? So before contact, if it's 5 coulombs, it will be 5. Even during contact, even after what? Contact, it remains the same. That is the principle of conservation of charge. Ne? Another thing that they can ask is grade 10 learners, right? They can ask you to calculate the number of excess electrons here. Remember, this sphere has excess of electrons, right? So how do we calculate the number of excess electrons in this sphere, right? The equation, we use the principle of charge quantization, right? The principle of charge quantization is NQE, right? So Q in this case is negative 7.2 times 10 to the power what? To the power negative 9. Then we're looking for the number of excess electrons times what? What is this QE? Is negative 1.6 times 10 to the power negative what? 19. Then you'll get the number of electrons in what? In excess, right? That is grade 10. It has nothing to do with Coulomb's law, all right? So there's so many things that we can talk about here. The grade 10, what we did actually in what? In grade 10. You can check which sphere has excess of electrons, which sphere has shortage of electrons. Electrons will be transferred from which sphere to which sphere if they were brought into contact, right? And again, calculating the number of those excess electrons, you know, calculating the number of electrons transferred. So please be careful. Here, I'm calculating the number of electrons that are in excess, okay? You can also calculate what? The number of electrons that are being transferred, right, from this sphere to this sphere, right? So how do we calculate the number of electrons transferred from this sphere to that sphere, right? In this case, what are you supposed to do? You need to, if you can calculate here, the change in charge. This is the first thing that you need to do. If they are brought into contact. Remember, here I was just calculating the number of excess electrons in this sphere. Let's say now they are brought into contact. Remember, if they are brought into contact, electrons are transferred. We can calculate the number of electrons that are transferred from a sphere from x to what? To y. So first thing that you need to do is to calculate what? Change in Q, change in charge, which is final charge minus what? The initial what? The initial charge, right? So final charge, in this case, our final charge, what? Final charge is unfortunate that our final charge will be what here? Will be 0. But let's not confuse, you know, Q after contact and Q net. All right? And then again, this is the number of electrons in excess in this sphere, right? Which is actually the number of electrons that will be transferred from this sphere to this sphere. All right? So these are some of the things that you need to know when it comes to, you know, such questions, or that you need to look at when it comes to these questions. So first question, they want us to state Coulomb's law in weights. So Coulomb's law in weights, we stick to the examination guidelines, right? So according to our examination guideline, what is Coulomb's law, right? The electrostatic force is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them, right? So the magnitude of the electrostatic force between point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. So that is Coulomb's law. Then next question, calculate the magnitude of the electrostatic force that Y exerts on X. Right. So this is Y. So this is X and what? And Y. Ne? This is where we have to start. Draw a free body diagram there. All right. So this, what am I having here? I'm having X and then Y. All right. So this is X. This is Y. X, Y. X is negative. This is positive. So there's force of what here? Of repulsion. So this will move, not force of repulsion, but force of what? Sorry, of attraction. So this will move towards. This is also going to move what? Towards. Okay? So this is the magnitude of the force that X. So here this magnitude and this magnitude, they're equal in this force and this force, they're equal in what? In magnitude, right? So this is going to be what? This one. The force, remember this is negative, ne? So this is going to be the force that Y exerts on X. Remember it's on X, right? So this is going to be the force that X exerts on what? On Y. These are the two forces, okay? And the force that Y exerts on X is equals to the force that X exerts on what? On Y, but acting in opposite what? That you can see the force that Y exerts on X is to the right, ne? And then the force that X exerts on Y is to what? Is to the left. But the magnitude is the same. The magnitude is the same, but acting in opposite what? Directions. So what are they looking for? Calculate the magnitude of the electrostatic force that Y exerts on what? On X. So the equation is F equals to K Q1 Q2 over what? Over R squared, right? What is our K? 9 times 10 to the power what? 9 times Q1, it can be X. And please, learners, be careful, ne? When we are dealing with this equation, your charges must be positive, even if the charge is negative. So you substitute by the positive here. So it will be positive 7.2 times 10 to the power what? To the power negative 9, right? Multiplied by 7.2 times 10 to the power what? Negative 9 again. Divided by the distance, which is 0.03 what? Squared. Let's not forget what? A square. Then we'll get our F in what? In, because they're looking for the magnitude, right? So if they're looking for F or electrostatic force, we're going to include what? The direction. The force that Y exerts on X. The force that Y exerts on X, the direction is to the right. But fortunately here, they're just looking for what? For the magnitude. But if they wanted us to add what? The direction, This is what we're going to do. All right. So first thing, if you're given a question on Coulomb's law, right? First thing, draw a free body diagram. So for each point charge. So for this point charge, the forces that these two point charges exert on each other, for X is acting to the right, for Y is acting to the left. This is the force that Y exerts on X. This is the force that X exerts on what? On Y. So what is the magnitude here? The magnitude is 5.184 times 10 to the power negative what? 4. So it's 5.184 times 10 to the power what? Negative 4 newtons. In which direction? To the right. But they are not looking for the direction. But where is this to the right coming from? From the free body diagram. All right. Then let's look at this one. 2-point charges A and B carrying charges plus 1.2 nanocoulombs, right? You can see, you cannot neglect this, is nanocoulombs, okay? It's nanocoulombs, all right? 5 centimeters. So there's a lot of conversion that we have to do there, right? So already I know if it's nano, this will be what? 1.2 times 10 to the power negative what? 9. This is also going to be what? 1.5 times 10 to the power negative what? 9 coulombs. This is in centimeters. Okay, it's 5 times 10 to the power negative 2 what? Meter. So I cannot neglect that. Because when it comes to that equation, F equals to KQ1, Q2 over R squared, my Q should be in coulombs and it should be a positive value, right? And then my R should be in what? In meters, okay? So that is why I've converted nanocoulombs to coulombs. That is why I've also converted centimeters to what? To meters, all right? Then an electron is placed at point X. There is an electron here at point X, which is 4 centimeters to the right of point charge A, right? So you can see that on the diagram. So between A and X is 4 centimeters. Between X and B, it's 1 centimeter. Between A and B is 5 centimeters. You can see that, all right? So how many point charges are we having here? 1, 2, 3. All right. And they're in one dimension. They're along what? A straight line. So there's an electron here. We already know the charge on an electron. The charge on an electron is negative 1.6 times 10 to the power negative 19 what? Coulombs. Where am I getting this from? From the data sheet. Let's go back to the data sheet. You will see what we are talking about. All right. Right. According to our data sheet, charge on an electron, it's negative 1.6 times 10 to the power negative 19 what? Coulombs. Right. Right. So charge on an electron is negative 1.6 times 10 to the power negative 19 what? Coulombs. Right. So this is what I have, right? Then here, learners, before the questions, what I want us to do here is to draw the free body diagrams. So if we are focusing on point X, which is an electron, there will be a force that QB exerts on X. There's a force that QA exerts on X. So we can draw a free body diagram for that. So that is X. Ne? So we have X there. So the force that the force between X and Q, which is QB, it's the force of attraction. Why am I saying force of attraction? X is negative, QB is positive, right? The force that X and QA exerts on each other, right? Is it the force of attraction or repulsion? It's still what? Attraction. Because QA is positive, but X is what? Is negative, right? So you have a force of what? Of attraction. Force of attraction between X and what? And B and QB. So force of attraction. So it's X. You focus on X, ne? X is attracted to B. B is this side, ne? So X is attracted to what? To B. This is the force that B exerts on what? On X. X is also attracted on what? On A. Yeah? So this is the force that A exerts on what? On X. Okay? This is the free body diagram. All right? X move. I know we are talking about stationary charges, né? But the focus is X. So just ask yourself a question whether X will move towards or away. So if it's attraction, X will move towards B, X will move towards what? Towards A. But if it was a repulsion, X was going to move away from B. Also, X was going to be move away from what? From A. If it was like charges. Okay. Then let's focus on B now. So let's say this is B. So between B and X, there's force of attraction. There's a force that X will exert on B. There's a force that A will exert on what? On B. So let's start with the force that X exerts on B. All right? So if this is B, will B move towards or away from X? It will move towards. There's attraction there. B is this side, X is here. So B will move towards X. So this is the force that X exerts on what? On B. Right, let's look at B and A now. Will B move towards or away from A? It will move away because it's positive, positive. So this is the force that B, not B, but A. This is the force that A exerts on what? On B. Force that A exerts on what? On B. Then the focus now is A. The focus is A. Will A move towards or away from X? It will move towards X. This is the force. We are doing that so that we'll be able to draw what? A free body what? Diagram. So between A and X, there is force of attraction. So obvious A is attracted to what? To X. So this is the force that X exerts on what? On A, right? Then between A and B, there is force of what? Of repulsion. Is positive, positive. So A will move away. So force that what? B exerts on what? On A. So this is where we have to start when we are dealing with what? Such questions. Ne? To start by drawing what? A free body diagram. So for X, this is X. What is is there a force of attraction or repulsion between X and B? Is attraction. So X attracted to B, X also attracted to what? To A. If this is what the free body diagram for B, what is the is there a force of attraction or repulsion between B and what? And X? There's force of attraction. So B attracted to what? To X. B, there's force of repulsion between B and what? And A. So it's where we have to start. We have to start by drawing what? A correct free body what? Body diagram, indicating the forces exerting on what? On each point charge. All right. So let's look at the question. State Coulomb's law. By now we know the magnitude of the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Then calculate the net electrostatic force experienced by the electron. The net electrostatic force experienced by what? By an electron. Where are we supposed to start? Draw a free body what? Diagram. This is X. There is what there? There is B. There is A. B is positive. Also A is what? Is positive. And this is what? Negative. So between X and B, there is force of what? Of attraction. Force that B exerts on X. Between X and A, there is force of what? Of attraction. So this is force that A exerts on what? On X. All right? Then you calculate the magnitude of each force, right? So F A on X is K Q1 Q2 over R squared, right? Which is 9 times 10 to the power 9 times Q1. It can be, the focus is A on X, ne? Your A, it's, what is the magnitude of A? It's 1.2, right? So it would be 1.2 times 10 to the power negative 9 times 1.6. You can see I'm no longer using negative there. So the magnitude of the charge when I'm using this equation must be positive, ne? So it's 1.6 times 10 to the power negative what? 19, all right? That is between A and X, ne? Over, what is the distance between A and X? The distance between A and X is 4 centimeters, which is going to be 4 or comma what? It's 4 times 10 to the power negative 2 all squared. Then we'll get our answer in what? In newtons. And what is the direction? Is to the left. All right? The direction is to the left. It's what we are focusing on. Then let's focus on this one, FB on X. FB on X. Q1, Q2 over R squared. 9 times 10 to the power 9. Then Q1, it will be, we can change that one to what? To QB, and then this one will be what? Will be X, ne? So QB, it's 1.5 times 10 to the power negative 9. Charge on X or an electron, 1.6, positive 1.6 times 10 to the power 19. So let's make sure when it comes to Q, Q must be positive and Q must be in coulombs, right? Then over R, our R, what is R between B and X? B and X is 1 centimeter, ne? So B and X is 1 times 10 to the power negative what? 2, or 1 divided by 100 all squared. Then you'll get your answer in newtons. And what is the direction? The direction of the force. The direction of the force, already we have the direction of the force, which is to the right. Okay, let's check the values. Here for the first one, I have 1.08 times 10 to the power negative 15, ne? So 1.08 times 10 to the power negative what? 15 coulombs. Sorry, 15 newtons to the left. And for the second one, what am I having? I'm having 2.16 times 10 to the power negative 14. 2.16 times 10 to the power negative what? 14. This is what we have, ne? So we have 1.08 times 10 to the power negative 15 newtons to the left for FA on X, and then for FB on X is 2.16 times 10 to the power negative 14 newtons to which direction? To the right. Then F net for forces in one dimension, it will be F what? A on X plus F B on what? On X, right? But you can see the direction is not the same, right? So they're acting in opposite direction, which means that here it will be what? FA on X, right? So it depends which direction are you taking as what? As positive, and which one are you taking as what? As negative. So let's take right as positive. So left will be what? Will be negative. So FA on B is acting to the left. So it's 1 point. So it will be negative 1.08 times 10 to the power negative 15 plus into plus, right? Because it's acting to the right. So plus into plus what? 2.16 times 10 to the power what? Negative 14, right? Then we'll get F net acting on X or acting on an electron as what? 2.052, ne? 2.052 times 10 to the power negative 14 what? Newtons in which direction? To the right. To the right. Okay? Okay. Right. Then, so, and then this question is out of how many marks? 5 marks. So, But first thing that you need to do is to draw a correct free body free body diagram. Then from there, make sure when you substitute in that equation, your Q is in coulombs and it should be a positive value. All right. Then if you check the question here, they are saying calculate the net electrostatic force. They didn't say the magnitude of the net. So if they say the net electrostatic force, that answer must have direction. So that is why I included the direction, which is to the right there. Another thing that they can do here, you have x, a and b in one dimension along a straight line, right? We can have a, let me go back, we can have a, x and b just like this, a, x, b, right? Your a, 1.2 times 10 to the power negative 9 coulombs. Your x, negative 1.6 times 10 to the power negative 19 coulombs. And then your b, it's 1.5, ne? 1.5 times 10 to the power negative 9 coulombs. The distance here is 4 centimeters. The distance here is 1 centimeter, right? So now they are no longer along a straight line. They are at right angles to each other, ne? So these are forces. Forces in 2 dimension. All right. So now they're in 2 dimension. So if, for example, they can say calculate the net electrostatic force, but they're in 2 dimension, or they're acting at right angles, the point charges, then again, first thing that you need to do is to draw a free body diagram. This is x, ne? So there's force of attraction between x and a, like this. This is the force that A exerts on what? On x, right? And then again there's attraction, you see? So there's force that B exerts on what? What is this? On x. Already we have calculated the magnitudes, right? The magnitude will be the same because I didn't change the distance, right? The magnitudes again are still the same. So the magnitude of this one is the same, and then as the one that we calculated. Even the magnitude of FB on x is the same as the one that we calculated. What was the magnitude? The magnitude of FB on x, we got 2.16. B on x, this one is 2.16 times 10 to the power negative 14 newtons. But now it's no longer to the right, ne? So it will be downwards, or south if you are using compass directions, ne? This one we got 1 point, if I'm not mistaken, 1.08, ne? Let's check here. We got 1.08, yes. 1.08. 1.08 times 10 to the power negative 15 newtons, right? But it's still to the left here, right? So, but now they're in 2 dimension, ne? For the previous question, they were in 1 dimension, right? Now they're in 2 dimension. So if they're looking for the electrostatic force here, you cannot use the same method as before, right? So for forces at right angles, or for perpendicular forces, or for forces in 2 dimension, right, we have to use Pythagoras theorem to get F net here. So the Pythagoras theorem will be F net will be equals to the square root of F A on B squared plus not F A on B, but F A on X plus F B on what? On X all squared, right? Which will be, what is the magnitude of F A on X? F A on X is 1.08 times 10 to the power negative 15 squared, right? Plus 2.16 times 10 to the power negative 14 all squared, right, you'll find your answer in what? In newtons. That will be the magnitude of the electrostatic force if they are acting in two dimension, or if they are acting at right angles, or if the forces they are perpendicular to each other. So you need to be careful whether the forces are in one dimension or they are perpendicular to each other. If they're in one dimension, it's F1 plus F2. Then make sure that you choose the direction, right? Or choose the positive what direction. But if they're acting at right angles or they're acting perpendicular to each other, to get the magnitude, you have to use Pythagoras what theorem. So here you'll get the magnitude, right? That is going to be using what? The Pythagoras what theorem. And then to get the direction, right? To get the direction, you did vectors into D, ne? Right? At the beginning of the year, vectors into D. So to get the direction, is either you find this angle, this is your free body diagram, right? So it's either you find this theta or the theta to the horizontal, ne? It's either theta to the vertical or theta to the horizontal. So theta to the horizontal, theta to the vertical. So it's up to you, ne? Or the angle to the vertical, angle to what? To the horizontal. Then, okay, let's check the angle to the horizontal. This is what I want us to do. So you have these two forces. This will be your F net, right? So let's find that angle. Already we know that this is force A on what? On X. This is force what? B on what? On X, right? So let's find theta. So use tan. So tan theta will be what? Opposite. Opposite side will be this one, which is FB on what? On X. And make sure that you use positive values also here, ne? Right? Over F what? FA on what? On X. So it's opposite over what? Adjacent side. So it will be theta will be tan to the power negative 1, right? Tan negative 1. Then FB on X. FB on X is 2.16. So it's 2.16 times 10 to the power negative what? 14 over 1.08 times 10 to the power negative what? 15. Then you find what here? You find theta in what? In degrees, right? So please be careful, or please make sure that you check whether the forces are in one dimension or they're in what? In two dimension. If they're in one dimension, net, how to calculate the net electrostatic force is F1 plus F2. But when it comes to the perpendicular ones, you use Pythagoras theorem to get, what is this? To get the magnitude, and then from there, to get the angle or the direction, you use tangent. Okay, so tan theta, then you check which theta. Rather, just find theta to the horizontal. Ne? So theta to the horizontal, it will be this over that. So it's opposite over adjacent, which is FB on X over FA on what? On X. So that is what Coulomb's law. That is Coulomb's law. I think we are done for today. So let's meet next week. And next week we'll still continue with what? With electrostatics. But the focus will be more on electric field. So today we are focusing on what? On Coulomb's law. Thank you so much.